We got electrons here, right? Got electrons in here. Got electrons here. Electrons here. Do I have electrons here?
No.
Not yet.
Now we do. All right, so again, remember, electrons are asked to move. We ask them to move. Now, when you plug something in and you turn it on, you are asking electrons to move. Now, can I have a fire between things that I'm asking to move? In other words, I have a parallel circuit and a series circuit. All right, parallel circuits run parallel to each other, correct? A series circuit would actually incorporate several different stops along the way in a series, like wall plugs, like maybe several different types of ceiling light. The can lights, they're series. You turn one switch, how many lights come on? Yeah, that's a series circuit. The lights are in series. All right, so we can have wall plugs that are in series. So don't say, oh, Instructor Black said you can't have a fire at a plug if there's no electrons flowing. Because we can have electrons flowing in that plug right there because we have something else plugged on the end of it. What I mean by that is, hey, it's got to have to be in series. So here's our breaker box. Here's our breakers. Here comes our branch circuits. Here's one receptacle. Here's two receptacles. Three receptacles. Alright, so now let's have a branch circuit for my lights. It's coming out of the box. This one's on this breaker. This one's going to be on this breaker. This one comes down. And here's my switch. And then it goes to my light. Terrible light, sorry. I was too busy drawing plugs. Both of these are really considered series circuits because I've got lights that are in series. And again, this is supposed to be a light bulb. Sorry about the terrible drawing. Alright, so I got some light bulbs that are in series, but what I really want you to understand is this series. These both are in parallel, they're parallel of each other, but this is a series circuit where I've got several different plugs in a series. Now when I add all the where are the electrons at? They're hanging out, right? They're not moving. We didn't ask any of them to move, but do I have electrons here? Yeah. Sure. What about here? Yeah. Yep, and down here? Yep, and they're all just sitting there. All sitting there to move because there's no switch down there. There's the breaker. What if I trip the breaker off? Where's the electrons at now? They're back at the breaker. So if you can identify that this circuit was not on at the time of the fire, guess what you don't have? Fire in that circuit. Lights off at the time of the fire? No fire in the lights. Ceiling fan off at the time of the fire? Maybe some electrons up there if it's a pull chain though. That's the way you got to think though. Where are my electrons? Are they hanging out at a switch or are they hanging out at a plug waiting to be asked to move? Alright, so I'll plug something in right here. Let's plug a lamp in. Where are my electrons moving then? They're moving here to here to here to here. So they're going pop, 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 and then back down. Alternating current. Are they moving down here? No. Is it still energized down here? Absolutely. Alright, so that's a good lamp. I'm good with that. Let's plug a lamp in down here. Now where are my electrons moving? The whole thing. Well, I don't have anything plugged in here.
Still flowing through it.
It's flowing through it because it's in series. That's right. All right, so now, theoretically, if I have a loose connection right here, what do I have? I have a potential fire hazard. Because resistance creates what? They're having a problem. It's resistance. Electrons are struggling to get through that whatever. Maybe it's an air gap from a loose connection. Maybe the loose connection caused some corrosion, some oxidation. And now they're struggling to get through that. But it's not an arc, correct? But, so what's going to happen? Surely my breaker is going to sense that I have a problem and turn itself off. Right? Not always. And you know what? Not at all. Until it creates an arc that goes to ground, our breaker's never going to know the difference. It's just going to seep on sending electrons. And the heat's going to do what? Keep on building and building and building until eventually we have a fire. So what I mean by that is, we got it here. We'll turn on a few of these things. Everything else should be working. Turn off this one. What's going on? I'm creating some resistance.
Yeah.
Why in the breaker tripping?
Because at the box is still pushing what it should.
I'm not grounding it to ground, right? I'm just asking these little, look at this. I got smoke appearing. What's happening? I'm converting something to a gas. That's what you need to understand. I did create a spark, but it didn't go to ground. I just got resistive heating. You know, it's not doing its job. Fried my circuit. But it didn't trip the breaker. Breaker's still ready and active. What you need to understand is it didn't go to ground. The circuit is still open. It's still asking electrons to go. We just have a loose connection. But it can create some arcs, it can create some sparks, it can create heat. This was getting hot in my hand, I can almost no longer touch it. But it didn't go to ground, so it didn't trip the breaker. So this can continue to go on. This can continue to occur. It's resistive heating. It's having resistance. It doesn't like what I'm doing. It's got a gap there. It's having to stop and start, stop and start. And all the electrons are trying to go and do what? All of this work. There's a lot of work for it to be done. Now, I mean, I pray nobody does this kind of stuff on it and use this much stuff. You know, but hey, people think that there's 6 plugs, they can use 6 things. Thought maybe I might have tripped the building circuit. I've done it before. All right, but again, that's what, so let's try to take a heat measurement. I just tripped that circuit right there. All right, Fahrenheit, Celsius. I can't read Celsius, I'm sorry, I'm going to have to read Fahrenheit. All right, so it's 86 degrees, so it's done cooled down since I was holding on to it. All right, so let's try to recreate that. 90. 95. 102. 117. 125, I'm going to trip it. My breaker didn't trip. Good to go. I just tripped that little thing down here. But if that thing wasn't tripping and we could keep on going, this thing could just escalate in heat, temperature, because it's resistive. It's just having trouble getting through what I'm doing to it. And that's what you need to understand, this loose connection. But hey, do I have anything plugged into it? No. This is that same circuit I just drew on the board. It's going from the breaker into this wire, into this plug, down to this plug, over here to this plug, and down and out. But I'm having a problem here. So don't get focused on nothing plugged in, no problem. If you got a V pattern coming off that, or if that whole wall is burned and you just have some melted up wires right there, find out if this is a series circuit and find out what's plugged in on the other end. This could be your whole problem right here. And it's probably going to be burned away. Because this kind of heating, it's like welding. Who does arc welding? Why doesn't it trip the breaker? You know, the same principles apply. It's manipulating the system so the breaker doesn't trip because we're not going to ground. Well, you are on arc welding, but it doesn't go to ground in a sense.